All right, so f of 2 pi and f of pi. And we'll just talk
Right.
about one of those because they're very similar. What does f of 2 pi tell you?
The full area from pi over 2 to 2 pi.
What kind of area?
The signed area.
Okay, so signed area accumulated from what two places?
Pi over 2 to 2 pi.
Right, so x equals pi over 2 to x equals 2 pi. So good. And then f of pi, I think y'all can fill in the blanks on that one. All right, so that's part B, right?
Right.
All right. What's next?
So then we were asked to define a function g of x that would give us the total accumulation of signed area from x equals 0.
Okay.
And the first way that we can do that is using an integral.
Okay.
And I actually accidentally deleted that, but it would be an integral from, wait, now I'm confused. I deleted that. I'm sorry, I'm gonna skip that.
That's okay.
Okay. And then the second way that we were able to do that is by doing f of 2 pi minus f of 0.
Okay. And the reason you can do it like that, I mean, even though f starts taking area at a place that's not really the beginning of your interval, if you go from pi over 2 to 2 pi, that's what f of 2 pi is. And then what f of 0 gives you is the area basically from here backwards. Assuming this right here is pi over 2. But when you have an integral where the upper limit is less than the lower limit, you basically you're going to get the opposite. You're going to get the negative of what you're expecting, which is why we're subtracting it here. Someone else from group 1, fill in the blanks in this integral for me. So we can also use an integral to find this signed area on that interval. What would that integral look like?
So would the integral be from 0 to 2 pi?
Let's do 0 to x so we can choose x.
Okay. And it should still be pt, right? P of t.
PT dt. Yep. Yeah, PT is the rate of change. So that's exactly it. And then part D, what was that one asking for? Was there a part D for this?
Yeah, I believe it's asking for the unsigned area, right? The area of the region below the x-axis.
Okay, so I want the area down here, right?
Yeah.
So how would I find that thing? So did you happen to find these two values right here? Those x values where it crosses the x-axis?
We didn't get that far.
Okay. So basically there's a couple ways you can do this. Since you have that g function, you can do g of, we'll call this x2, and we'll call this x1, x2. You can do g of x2 minus g of x1, or you can do an integral from x1 to x2 of pt dt. Either one of those will give you that area.
Okay, is that like a good answer to put?
No, I mean, I really want to know what those points are.
Well, it was a little bit of work, but sorry, I'm not from that group.
Right, but if you were in group 2, then you need to define those.
Yeah, they're just a little complex. I couldn't find it on my own.
Okay.
The points for those are 2 pi divided by 3. Yeah, they're 2 pi divided by 3 and 4 pi divided by 3.
Yep. You have to solve a couple of trig equation to get those values there. But yeah, those points are 4 pi over 3 and 2 pi over 3. So now I trust that integral. Any questions on number 1? All right, thanks everyone. Let's go ahead and look at problem number 2.
I guess I can explain it.
Okay, go for it. You want to share something or you want me to write?
Can you write it? I did this all on paper.
Not a problem.
So what I figured out is that since you can't use an absolute sign, you have to do it in 3 different integrals. So the first integral would be the integral from 0 to 2 pi divided by 3. Then the function, and then it would be plus 2 pi divided by the integral from 2 pi divided by 3 to 4 pi divided by 3, then the function, but that would have to be negative since the answer for that would be negative, so you want it positive. And then the last integral would be 4 pi divided by 3 to 2 pi, and that would just be the normal rate of change, P of t.
So I'm sorry if I was behind, but I think this is what I heard.
Yeah, just the only thing that's missing is the negative sign for the 2 pi divided by 3 to 4 pi divided by 3.
Okay. And why does that have to be negative?
Because the answer for 2 pi divided by 3 to 4 pi divided by 3 is negative, so you want to cancel out the negatives to make it positive.
Yeah, good. Yeah, if you want, remember, unsigned area means I treat all areas as positive. So I definitely want that area below the x-axis to be treated as positive, which means I have to negate the negative. All right, did you say you were also working on a piecewise function to do this?
I thought about it, but then I was just like, if I can just use 3 and I'm going to do a piecewise.
Okay, so just in case you might have to worry about this for tomorrow, let's do a piecewise function here. So again, we got to do this in 3 intervals. So the first interval, that's going to go how far? From 0. How far right can I push this first interval?
2 pi over 3.
2 pi over 3. And that first one's pretty simple. I can just integrate from 0 to x of pt dt. My next interval is going to go from 2 pi over 3 to what? What's the right bound of that?
4 pi over 3.
4 pi over 3. Now be careful. What am I going to integrate here?
You're going to integrate from 4 pi over 3 to x.
Not from 4 pi over 3 to x. I'll give you a hint here. I'm going to start writing this integral way over here. So from 2 pi over 3 to x of pt dt. But if I just use that integral by itself, I'm only going to get the area in the middle. So what else do I have to include to make sure I get all the area on the left?
Would you have to include a 2 pi over 3?
Yeah. So yeah, you could use function notation, say a 2 pi over 3, but I probably shouldn't say a of x equals a of something else. So I'll just put this integral here. So the integral for over the whole 0 to 2 pi over 3 of pt dt. And then I want to subtract this one because I know that'll be negative and I want it to be positive. So I suspect that you might be catching on to what this last one's going to look like. What would this last piece of this function look like? So again, I'm going to have my 0 to 2 pi over 3 of pt dt. I'm still going to have this minus this negative integral. But instead of putting the variable there, I'm going to sweep it all the way to 4 pi over 3. And then I finally have to include my current interval from 4 pi over 3 to x with pt dt. So those are two good ways to represent that area there. Any questions for that one?
So it looks like, okay, I'm getting a little lost here. So it looks like you're subtracting the value before it from the value after it. Is that correct?
Are you talking about the piecewise function or the first way I showed it?
Specifically the last part of the piecewise function, like on the very bottom.
Okay,
I'm just having trouble following it.
sure. So remember, we want unsigned area. So I want all areas, whether they're below or above the x-axis, to be treated as positive.
Mm-hmm.
So the first integral, that's going to give me my first, this black piece here. This second integral here from 2 pi over 3 to 4 pi over 3, that's going to give me an area, but the area it is going to give me is going to be negative.
Okay, so we don't want to make it positive, or
Well, that's why we're subtracting it. Because we recognize that since that area is below the x-axis, that integral will give us a negative.
Oh, okay. Sorry, yeah, I'm just.
Oh, that's a good question.
I just saw so many in my brain. Okay, I need to ask.
I'm glad you did. That's a good question. Anything else on number 2?
Can you scroll up just for a sec? All right, thank you.
Yep. And I'm gonna send this note file out.
So in the piecewise function, I see like multiple integrals where it integrates 2x, like from 1 to x. You know what I mean?
Yeah.
Why is there like multiple 2x intervals?
What do you mean by multiple 2x intervals?
Like so the first one at the top, it's 0 to x, and then below that you have the second interval, and that one is 2 pi over 3 to x.
Okay, I got you. So let's say I want to find an area, an unsigned area from 0 to pi. If I want to do that, then I need to integrate all this stuff here. Wait, that was 2 pi over 3, right? Yeah. So I want to integrate from 0 to pi. I have to integrate all of this stuff in here, but that still won't be enough. So then I have to begin integrating this area here. And since I want unsigned area, and part of this area is going to be negative if I just use an integral, I have to change the integral I'm going to use.
Okay.
Basically, then the only real change I have to make is I have to make that one negative. By putting a negative sign on that one, I will make all of its values positive.
Okay, I got you.
Good questions. What else? All right, I'm going to give it over to group number 3 here. Let me know if you want me to keep drawing or if you have something to share.
I have something I can share.
Okay, then I have to stop.
It'll be easier.
All right, go for it.
So basically we just took the graph of p of x and graphed it. And then if you were gonna rotate it around, that's kind of the shape you'd get.
It's a good visual.
So if you're dividing it on delta x in the x intervals, the like cylinders are going this way, so they'd be increasing by height. So you're using the pi r squared for rate of change. So that's what this function is. And then you just kind of take the integral of it to get the volume.
So one thing I want to focus on here, I mean, this is exactly right. But a question I want to ask you all is this. Do we understand why we're using the area of a circle for our rate of change function instead of that lateral surface? Well, I'll just kind of briefly explain it, even though I'm not getting any questions on it. Since we're moving from, what does Nicholas say? Our cylinders are over the interval are increasing by height. So that's absolutely true. As x increases here, I'm increasing my height, which means I'm adding, basically you can think about it, I'm adding circles onto the right here. So that's why that's the area you need to be thinking about, is the pi r squared. And the radius is just given purely by my y value, and I know exactly what y equals. So that integral is going to work perfectly. Any more questions on number 3?
So if it's in x intervals, is that always going to be increasing by height, or how do you determine whether it's a height or?
So it depends on 2 things. What variable am I integrating on? Is it an x variable or is it a y variable? Also, you need to know, am I rotating around a horizontal axis or a vertical axis? So in this case, because I'm using x as my variable and rotating around the x-axis, that combination of factors tells me that growing x will grow my height.
Okay.
But yeah, knowing x is not quite enough there. All right. Anything else on 3? All right, I'll give it over to group 4 then. Group 4, I think I had a communication breakdown there. Did you all get number 4 done?
Yeah, I managed to get something.
Okay. Do you want to share or do you want me to write for you?
Can you write for me?
Yeah, not a problem.
So for the arc length of the graph of p as a function of x, on lecture Monday, we saw that the rate of change of arc length of a function would be the square root of 1 plus p prime x squared. So for s of x, that would equal the integral from 0 to x of the square root of 1 plus p prime of x squared dx.
So I got to catch up to you. So it's the integral from what to what?
0 to x.
Okay.
Of the square root of 1 plus p prime of x squared. And then dx.
Okay, this is almost perfect. I have one small but important complaint about this. Anybody see what I'm talking about?
2p
I think you cut out, Serena.
of t dt. Do p prime of t dt.
Yep. There you go. Yeah, we don't want to use the same constant or the same value of x that we're integrating until as these, which are things that are really changing and growing over an entire interval. So I'm gonna, I think it's worthwhile. I mean, I got 1249 right now, but if people have questions about the arc length thing, I think you should ask them because, you know, we only touched that for like 20 minutes in a lecture yesterday. Any questions about how this arc length integral got developed?
Well, I have questions about the function, the root. How did you get that function, like 1 plus?
So do you remember in lecture on Monday, the way Mark developed this integral was basically it comes down to, you know, you taking you taking a function and, you know, at regular intervals, basically you'll draw a tangent line segment at those intervals. So basically what you're doing with that is you're breaking up your function into a bunch of little tiny straight lines. And then from that, you are basically taking your slopes of those tangent lines and using the Pythagorean theorem to add up all those little tiny lengths together. So you know your change in x is going to be dx for each one. And you know your change in y is going to be dy for each one. But if you're using a constant rate of change, a constant slope, you know that dy is equal to m dx. I think the way that Mark explained that on Monday was really thorough and really good. And I think now that you've had some time to kind of reflect on it, either consciously or unconsciously, I would really recommend doing a couple of things before tomorrow. Go back and rewatch at least the last 15 minutes of Mark's lecture from yesterday to see the way he develops this. I think it's going to be more valuable for you to see where the integral comes from than just memorizing how it works. Also, I'm going to send out the video, or I'm going to post both those videos on YouTube for my recitations today. I recommend not only watching the one from this class, but watch the one from my morning class, just because you're going to see things from different angles with a different group. But, you know, talk about unsigned area, signed area, volume of revolution, and arc length. Those are all things that are definitely going to be on that exam tomorrow. Any last minute questions before I let you all go?
For the second part of number 4, where it asks for the total length of the graph of P between the interval, can I check my answer on that?
Yeah, I didn't know there was a second part to that one.
Yeah. It's not like a part A or anything. It's just a.
Okay, express using function notation the total length of all the graph of P between 0 and 2 pi. That's above the x-axis. Sure. What would you say for that?
I would say s of 2 pi minus the difference of s of 4 pi over 3 minus s of 2 pi over 3. So you're just subtracting the difference of the arc length in that interval below the x-axis.
So s of 2, okay. Yeah, I agree with that.
Okay.
So this right here would give you the area to the right of that. Just to make it a little more clear. That right, this parentheses, this is the area to the right of where you dip below the x-axis, right? And this, I'm going to put one more term in here even though you don't really need it. Don't really need that because s of 0 is, of course, 0. But this right here would be the area to the left of this point right here where you dip below the x-axis. Yeah.
Why would you subtract them then?
Oh, good point. Good catch there. Yeah, that would be an addition.
Okay.
Oh, sorry. I meant to. Could you put it in parentheses, like minus the difference between the arc length in that negative interval?
So what you had is this, s of 2 pi minus, like this?
Yeah.
Yeah, that's mathematically identical.
Okay, cool.
Yeah, good catch on the sign flip, though. Anything else?
Just a question. What do we turn in for the recitation today? Because I'm looking at Canvas right now. It doesn't. There's no submit button or anything.
Right. If you were here, you're gonna get credit.
Cool.
So I got a screenshot of who was here. As far as I see it, you all did plenty of work and shared it with us. So I'm happy with that.
All right. Thank you.
Okay. Thank you all, and I'll see you tomorrow. Have a good night.
Can I ask a quick question? I'm sorry.
Oh, no, go for it.
For arc length, is this the extent that we're, like, are we supposed to be able to do any more with it? Or is this all that we're responsible for.
So I mean, this is really all that Mark has shown you, and you know, arc length is a pretty limited application of the integral. There isn't much more to do with it. I mean, its only real use is to find the length of a curve, which is what he showed you how to do with it. So I mean, it's very useful in a very limited set of cases.
Okay, thank you.
Thank you.
I just had a quick question. So on the test tomorrow, are we able to use a graphing calculator?
I actually don't know. I know Mark was unsure about that. Let me see if I can get him to make an announcement.
I saw on the latest announcement that it said that like
Oh,
a
you know what?
normal-
You're right. So as long as it's not one of the overpowered ones like TI-89 or any of the ones that can solve equations for you, but like a TI-83, TI-84, those are fine.
Okay, cool. I got it.
That's my fault. I did see that.
All right, thank you.
Thank you. All right, everyone. I'm talking to no.